Hi there, this is Mrs. Hammer. Thank you for joining me. Today we're going to be talking about equilibrium with acids and bases. So the first thing to understand before we get into this is to remember that the vast majority of acids and bases are weak. We have a very short list of strong acids and bases. Anything else is a weak acid or base. And what this means is that they do not ionize much and will eventually come to equilibrium with their ions. So if you have a weak acid, and we're just going to give a generic formula for an acid right now, HA. That could be HF, HC2, H3O2. It's any hydrogen paired up with an anion that creates a weak acid. So we're just going to call it HA. It reacts with water. Remember, the acid kind of throws away its hydrogen, gives it to the water. So we get the hydronium and the anion. Sometimes we're going to leave out the water and just show this equation here. The main idea is that it's got this double arrow, and that double arrow indicates that we don't have 100% completion of this reaction. We still actually have a lot of the original acid left over and very little of the ions produced. So if you have 1 molar acid, you're not actually going to get 1 molar concentration of the hydrogen ion. So we're going to talk today about how to actually go about calculating how much you get. So in order to do that, we have to have this thing called the equilibrium constant, or the equilibrium constant expression for a weak acid. So it's essentially just some number. That's the thing to remember, is that this is a number. It's some very small number. It's very less than 1. And it is the concentration of the hydrogen times the anion divided by the concentration of the acid. Okay, so the brackets like this mean molarity. And so if we know the molarity of the 2 ions and the molarity of the acid, after it's ionized as much as it's going to, and we plug those values in, it's going to be less than 1. And again, it's going to be some number. It might be 4 times 10 to the negative 4. It could be 1.2 times 10 to the negative 15. It's just a number. For bases, the same thing applies. Bases, weak bases have this double arrow indicating that they don't completely ionize, they don't completely react. So we're going to go with B for our general base formula, but again, that might be NH3 or any other weak base. And so bases take hydrogen. So this base is going to take a hydrogen from the water and form Hb+. So there's one of your ions that it forms, and OH-. That's what makes it the pH actually greater than 7. So again, the general equilibrium constant for this is the 2 ion concentrations over the base concentration. So if we look at both of them, both the acid and the base equilibrium constant expression, we see that it's the products, the ions, because the ions are on the product side for both of them. There were the products, the ions, divided by the original acid or base concentration, which was the reactant. Okay. So you might want to write this down. You might want to pause it and write this down. Ka or Kb is set up by putting the concentration of products over the concentration of the reactants, and pure water is left out. Again, you might want to pause and write that down. So points to ponder in relation to these K values. What does it mean that the K value is less than 1? It means that the fraction is less than 1. We have products over reactants. In order for this value to be less than 1, we have a lot of reactant and a very little product. Okay, so maybe for every 1 product we have 100 reactants left over. So that's what it means that it's less than 1. We get very little product. Remember that the brackets mean molarity. Okay, and it's important for me to point out that the concentrations that we're going to plug in, so the actual values that we're going to plug into this fraction, are at equilibrium after the acid or base has dissociated to its maximum amount. Okay, and again, I'm going to point out that water is not included. So we're going to do a little bit of practice. We're going to finish the dissociation reaction, and we're going to write the K expression. So let's do this first one together. We have HI, and so that's going to split apart, give away its hydrogen, and then the iodide ion is left over. So that's our first task with these, is essentially just throw out a hydrogen ion and we have leftovers. For our Ka expression, we're going to put products over reactants, and we're going to put them in brackets to indicate that we're talking about molarity. So it's going to be the hydrogen ion times the iodide ion divided by the original hydriodic acid. Okay, and that's it. Okay, put the 2 ions divided by the original acid. That's your K expression. We're going to do more with it later, but for now we just need to be able to set it up. So you might want to pause and try these next 3 on your own. All right, so finishing these out, we have 3 K expressions. Essentially in all of them, the acid gave away its hydrogen, and then we had anion over the original acid or base. These bottom 2 were different because we did include water. So rather than producing hydrogen, we produced hydronium, but that's the ion that went in. But remember, those are essentially the same thing. And remember that we omitted water when we wrote the K expression. So that's our first skill that we need to do. Now we're going to do the same thing for bases. So we're going to finish the dissociation and then write the K expression. So bases gain a hydrogen from water. So all of these, we have to show water in the equation over here. They're not going to go in the K value, but we have to show the water because that's where the base gets its hydrogen from. So we take a hydrogen, give it to the base. So this becomes NH4 plus, leaving behind OH minus. So we are going to essentially put products over reactants. So that's NH4 plus times OH minus, and then NH3 goes on the bottom. We left out the water, and that's it. So feel free to pause and try these next 3 on your own. All right, so this is a good time to check your answers. Remember that we omitted water from the KB expression over here. And pretty much for all of these, our original base gained a positive hydrogen ion turning into this right here. So feel free to pause it and check your answers before you move on. All right, the K value, what does it do? It helps us determine how much of the acid or base will actually ionize, and the amount that does ionize we call X. We're going to use a Rice table that we learned about in the solubility chapter that we just finished to organize our calculations. There's 2 basic types of situations here. Again, the 2 variables we're going to have, the K value and X, the actual molarity amount that ionizes. If you need to calculate Ka or Kb, you have to be given X, or it could be vice versa. If you have to calculate X, you have to know Ka or Kb. So I think the easiest way to get understand these problems is look at an example. So here's a completely spelled out example for us. Hydrogen cyanide is a weak acid and a notorious poison. Calculate the hydrogen value in a 0.5 molar solution and calculate the pH of the solution. Ka is given. So Ka, like I told you a while ago, is a number. And this is the number for this particular acid. So to organize our calculations, we're going to do this thing called a Rice table. So RICE, and this is what they all stand for. So the reaction is just showing the acid ionizing. So it's what we've been practicing. So the HCN gives up its hydrogen. Again, we're going to omit the water. Forget about the water. Doesn't matter. It turns into H plus and Cn minus. So initially we had 0.5 molar. That was given in the problem. 0.5 molar acid right up here. We had no ions to begin with. This is like when we start the clock. X is how much is dissociating. So that's the change. So the 0.5 molar acid is going to decrease by some amount. Okay. The hydrogen and the cyanide are going to increase by that same amount. Okay. Now, what we're going to do here is we're going to simplify something. We're going to say that this acid ionizes so little that this 0.5 minus X is still essentially 0.5. It's losing so little that it's still essentially the same amount. So if you consider someone who has $50 billion and they lose $100, like they lose it, it's just gone, they're pretty much still a 50 billionaire. So we're going to omit this little minus X, okay? So what we're going to do is we're going to substitute the equilibrium values, so that's this last line here, the equilibrium values, into the K expression. And we're going to omit that minus X. So the hydrogen and the cyanide were both X, so we're going to have X on top in both of these spaces. The HCN was 0.5, and it lost a little bit, but it's still pretty much 0.5, so we put that there. So we pretty much just solve for X here. So we have 6.2 times 10 to the negative 10 equals X squared over 0.5. We want to solve for X because X is the amount that actually ionizes, okay? So we're going to go over to our calculator. And so we're going to type in 6.2 times 10 to the negative 10. I always do it in parentheses. 6.2 times 10 to the negative 10 And then to solve for x squared, first we need to multiply by this 0.5. Okay. And then we need to square root our answer to get just x. So we're going to square root our answer. Okay, so we get 1.8 times 10 to the negative fifth. That's our x value. So 1.8 times 10 to the negative fifth. That's x. Okay, the problem never says solve for x though. It says calculate the hydrogen concentration and calculate the pH. So this will be fairly easy. If you think about it, the hydrogen ion concentration is x. So it's 1.8 times 10 to the negative fifth molar. And then finally, to go from hydrogen ion concentration to pH, remember that we negative log that value. Negative log of hydrogen equals pH. So we're going to go back to our calculator. And negative log, you can just use the answer function here in the calculator, 4.75. And that's a pretty reasonable pH for a weak acid, 4.75. Okay, so that's kind of the gist of how these problems work. The main idea is always set up a rice table to kind of organize the information that you're given. So let's try some more. Oh, and it is worth noting that base problems work exactly the same way, but when you solve for x, it's going to be the hydroxide ion concentration. We'll look at an example of that. All right, let's do this one together. The weak acid hydrogen fluoride can be used to etch glass. If you're in my class, you know that that might be among other things, according to the TV show Breaking Bad. In a 0.25 molar solution of HF, the fluoride ion concentration is found to be 0.012 molar. So that's the fluoride ion concentration. We're going to solve for Ka. All right, so this is the different situation. Ka is not given. We're going to solve for Ka. But you always begin by organizing your information in a rice table. That's the easiest thing to do. So you start with your reaction. Just write the acid reaction, the hydrogen breaking off the acid, forming that anion. Okay. So now let's sort through what we have. We have a 0.25 molar solution of HF. So that was our amount of HF, 0.25 molar. And the ions always started at 0 because it hasn't ionized yet. Okay. In that solution, when it does produce fluoride, the amount of fluoride is found to be 0.012. So I'm going to put that in the final E line down here for fluoride, 0.012 molar. Okay. Now, we have enough information to actually fill out the entire rice table. So the fluoride started at 0 and ended at 0.012. So the change was plus 0.012. Now, because hydrogen and fluoride have the same coefficients, they're going to increase by the same amount. So the hydrogen is going to go up by the same amount, 0.012. Well, it started at 0, increased by 0.012, so it is 0.012 molar. And if the ions were increasing in value, the original acid was decreasing or ionizing, so minus 0.012. Okay, so we can actually calculate the final value of the HF. We're just going to subtract. So 0.25 minus 0.012, 0.238. 0.238 molar. So we see that it decreased by just a little bit. All right, so we're going to calculate the Ka value. To do this, let's set up that K expression that we practiced in problem 1. You put the ions, H plus and F minus, over the original acid, HF. And remember that we substitute the equilibrium line in to get the equilibrium constant. So Ka is going to equal 0.012, that's the hydrogen, times 0.012, that's the fluoride, divided by 0.238, that's the HF. So we're just about here. Let's get our calculator back one more time and calculate this. 0.012 squared, or just multiply it again, 0.012, and divide by 0.238. So Ka is 6.1 times 10 to the negative 4. 6.1 times 10 to the negative 4. Think about your answers. Remember I told you that Kas and Kbs are always going to be less than 1. So that fits with what we know. All right, finishing this out. We've done our hard stuff. We've done our equilibrium. Now we're just doing some final calculations. What's the pH of the solution? Well, pH is the negative log of the hydrogen concentration. Well, what's the hydrogen concentration? It's from the rice table, 0.012. So it's the negative log 0.012. So get our calculator back. Negative log 0.012, 1.92. Again, it's a reasonable number. That's the pH of a weak acid, 1.92. All right, that's the pH. And final question, what's the hydroxide ion concentration? The easiest way to do this is use the formula that relates hydrogen and hydroxide that we talked about in class. They always multiply together to give you 1 times 10 to the negative 14. So substituting in, the hydrogen was 0.012. Hydroxide, we don't know, equals 1 times 10 to the negative 14. So we're going to solve for our hydroxide concentration by dividing. So 1 times 10 to the negative 14, close parentheses, divided by 0.012. 8.3 times 10 to the negative 13. 8.3 times 10 to the negative 13 molar. All right. So that's a great example of a weak acid problem and all the different kinds of things you could figure out doing that. Okay, let's move on. Another example. Benzoic acid ionizes to form the benzoate ion. The Ka value is given. Okay, again, if the Ka value is given, we're usually going to be solving for X, or the hydrogen amount. Okay, so first off, write the Ka expression. Now, I've bolded this hydrogen because there's more than one hydrogen, and I wanted to show you which one breaks off. So C6H5COOH is going to turn into C6H5COO minus, and then a separated off hydrogen. So if we write the K expression for that, it's going to be, I like to put the hydrogen first. Hydrogen times the benzoate ion, C6H5COO minus, over the original acid formula, put back together again, C6H5COOH. So that's our answer for the first part, this expression over here at the end, this fraction. Next, calculate the hydrogen ion concentration if the benzoic acid was 0.04 molar. So this is where we get into the rice table. We don't know how much hydrogen is going to be produced. It depends on the K value. So organize your calculations with rice. So we write our reaction C6H5COOH, double arrow, that should be a double arrow, Miss Hammer, produces H plus, and then C6H5COO minus. Okay, what do we know? We know that the acid before it ionized was 0.04 molar, 0.040 molar. We know that these always start at 0. That'll never change. All right, we have no idea how much it's actually going to ionize. Not a clue. We didn't have any other information other than the Ka value. So we can simply say that it's going to lose some, and this is going to gain by the same amount because all the coefficients are 1 to 1 to 1 ratio. So the benzoic acid is going to be 0.040 minus X, but same as before, that minus X, just forget about it. X and X. So we have our whole rice table filled out, and now we're going to substitute this final equilibrium line up into the K expression. And we're also going to substitute our answer, or not our answer, our value for Ka. We know what Ka is. They told us up here. It's 6.3 times 10 to the negative fifth. So 6.3 times 10 to the negative fifth equals X squared over 0.040. Okay, so now we go grab our calculator. .3 times 10 to the negative fifth times 0.04. Okay, and then we have to square root it to get rid of the X squared. 0.0016. X equals 0.0016. They didn't ask for X though, they asked for the hydrogen ion concentration. Well, X is the hydrogen ion concentration. So that's our answer here. All right, our final part is what percentage of the original acid actually dissociated. This is something called percent dissociation. So the amount that dissociated was X, 0.0016. And the original amount that we started with was 0.04. So we just find that percentage, part over whole. So it's going to be 0.0016, the part, over the original amount, 0.040, and it's a percentage, so we're going to multiply by 100. This value is usually fairly small, usually less than 5%. That's the definition of weak acids. They barely dissociate. So let's go back to our calculator and do this final calculation. 0.0016 divided by 0.04 and multiply by 100. I could have done that in my head. 4%. So there we go. Again, all of our answers here are making sense. Our percent dissociation, the amount that dissociated in a weak acid, is 4%. That matches our less than 5% rule. All right, so our next problem is going to be different because we're dealing with a base. So this one says, let's get to a good color. A chemist creates a 0.2 molar solution of ethylamine. So this is our chemical. The Kb of ethylamine is given as 5.6 times 10 to the negative 4. So you may not be able to look at this and know that it's a base, but they gave us a Kb, so we know it's going to be a base. So we're going to calculate the hydroxide ion concentration actually produced at equilibrium. So it's going to be less than this 0.2 molar because it's a weak base. So we organize our calculations with a rice table. So C2H5NH2 is going to react with water. You have to show water on base reactions. I've said that before. And so it's going to take a hydrogen from the water. So it's going to form C2H5NH3 plus and leave behind the OH minus. So we're going to start out with no ions, and we're trying to figure out how much hydroxide is produced. So that's our goal. The water isn't going to matter. It doesn't go in the K expression, so I usually just draw a little squiggly line down the rice table. And the starting concentration of the base was our 0.2 molar, so 0.20 molar. All right, the process from here on out is pretty much the same as with an acid. We don't know how much is going to dissociate. It's just going to be some amount. But we know that this is going to increase by the same amount because it's all a 1-to-1 ratio. So the two ions are going to end as X molar. We'll solve for that. And the base is going to be 0.20 minus X, but in a weak acid or base problem, that is always negligible. So we always cross it out if it's a weak acid or base problem. So we're going to now use our Kb value to solve for X. So Kb is going to equal the C2H5NH3 plus times the OH minus over the C2H5NH2. And things that I like to remind everybody about is we're plugging in the equilibrium values right there. And the Kb value was given. So Kb is 5.6 times 10 to the negative 4 equals the two values on top in the rice table were both equal to X. So it's X squared over 0.20. And we're going to grab our calculator, but I'm going to go ahead and think ahead. The question said calculate the hydroxide ion concentration. Well, the hydroxide ion concentration is equal to X. So essentially we're going to solve for X, and that's going to be our answer for the hydroxide ion concentration. So let's switch over to our calculator. So 5.6 times 10 to the negative 4 times 10 to the negative 4 times the 0.2 from the bottom, and then get rid of the X squared by square rooting. And so we determine that X is 0.011 with two sig figs, 0.011. 0.011 molar, because again, that's a concentration. I think I forgot to do that on a previous problem. It's the molarity of the hydroxide ion concentration. All right, so moving on. Part B is calculate the pH of the solution. Well, we're given the OH concentration. So if we negative log the OH concentration, that's going to give us POH. That's a good starting point. So let's do that. The POH is going to be the negative log of 0.011. So let's grab our calculator and solve for that. The negative log of 0.011. 1.96. 1.96. That is the pOH. Okay. We know that the pH and the pOH have to add up to 14, so I'm going to subtract that from 14. So 14 minus my answer, 12.04. pH equals 12.04. Again, it's good to make sure your answer makes sense. pH of 12 is absolutely greater than 7. That's a base, and we had a base, so our pH makes sense. All right, finally, what percentage of the base dissociated? So again, this is the amount that dissociated, which was 0.011 molar, divided by the amount that we started with, which was 0.2 molar. So the part dissociated over the original whole amount times 100, part over whole times 100. So 0.011 divided by 0.20 times 100. So 0.011 divided by 0.2 times 100, 5.5%. That's a little high for a weak base, but it's kind of within reasonable range. We typically say they dissociate less than 5%. Man, that's pretty close. All right, we're going to do one more practice problem. And this one is a little bit of a challenge. It's just presenting different information, so we're going to have to think a little bit more. So the pH of 0.016 molar aqueous solution of P toluidine, and we have this crazy formula, is 8.6. Calculate the Kb of the solution. Kb of the solution is telling me that this is a base. Okay, I'm going to be a little lazy, and I'm not going to write all this stuff out over and over again. I'm going to call this B for base. Okay, so these two things are now equivalent. So I'm going to set up my rice table, because that's just always a good starting point. So my base is going to interact with the water and form BH plus, because bases take a hydrogen, took it from the water and formed hydroxide. Okay. Looking through the problem, what do I know? The solution of the original base was 0.016 molar, so I'm going to put that in here, 0.016 molar. The water is not going to matter. I know the ions started at 0. And that's really all that's been directly given to me. I'm trying to calculate the Kb. That's going to happen down here eventually. I'm going to go ahead and set it up. It's going to be BH plus times OH minus over the original B value. We leave out the water. Products over reactants leave out the water. But again, I haven't been given anything to directly fill in the rice table. The only other piece of information I was given was that the pH is 8.6. That's going to be my starting point, okay? If I think about this off to the side, if I know the pH, I could go from there to the pOH, and I could go from there to the OH concentration. Well, look at that. The OH concentration would be this spot in the rice table, okay? So we're going to kind of do some side calculations over here, okay? So we're going to go through that process. If the pH is 8.60, I know that the pOH is 14 minus that. So 14 minus 8.6, 5.4. Okay, and then my next step to get the OH concentration, I'll actually write out this formula. It's 10 to the negative pOH. So that's going to be 10 to the negative 5.4. So let's calculate our OH concentration in our calculator. 10 raised to the negative 5.4. 3.98 times 10 to the negative 6. 3.98 times 10 to the negative 6. Okay, so this is our OH concentration. This is what I'm going to plug in here in my rice table. 3.98 times 10 to the negative 6. So I now know that the OH started at 0 and it ended at 3.98 times 10 to the negative 6. So that was the amount that it increased by. That's kind of a duh statement. Okay. But I know that the BH plus and the OH minus both started at 0 and they increased by the same amount because, again, that 1-to-1 ratio. So this is also going to be plus that value. So it's going to end at that value. So I know now my two ion values, I know those two values in the Kb expression. And now I need to figure out my base amount. I'm going to subtract 3.98 times 10 to the negative 6. And I'm going to go ahead and do that in my calculator. So 0.016 minus 3.98 times 10, let's go back, times 10 to the negative 6. I'm imagining that I'm subtracting a really small number. It's not going to change much. That's kind of why x is usually negligible, but we can go ahead and calculate it anyway. 0.015996. Let's go with 0.01599. 0.01599. See what I'm talking about? $1 billion, they lose a little bit. They're still pretty much the same. That's what we're talking about. Okay, so we're going to substitute in, solve for our KB value. We're almost there. Remember, plug in the values from the E line into your expression. So on top, I have these two ion values. They're the same. They're just going to be squared. So 3.98 times 10 to the negative 6 squared over 0.01599. Now I'm going to think in advance. I'm solving for a K value of a weak base. Should be a pretty darn small number. That's what we're looking for. So, oops, come back, calculator. All right, let's do this. 3.98 times 10 to the negative 6, square it, and then divide by 0.01599. We're hoping for a small number, and there it is. 9.9 times 10 to the negative 10. So KB equals 9.9 times 10 to the negative 10. That's our answer. Okay, so this one, the process was kind of the same in that we set up a rice table. Okay, you'll notice that all these problems that dealt with KA or KB, a rice table is the way to go for organizing your information. The only difference is what they told us. Okay, this one they told us the pH. In a previous one, they might have told us the final concentration of one of the ions, just straight out told us. They might have given us the K value and asked us to solve for these final concentrations. So what they ask for and what they give might be different each time, but the constant is that you always use a rice table when you're trying to solve these weak acid or base Ka, Kb problems. Thank you for watching. Thanks for sticking with it. I hope it was helpful. See you later.